Welcome to solverfy.
In this problem, we're going to shine light on a sequence of 3 different materials, each having its own index of refraction, N1, N2, and N3. We're given that the indices of refraction are N1 equals 1.5, N2 equals 1.34, and N3 equals 1.42. We're also told that the thickness of the middle layer with index of refraction N2, which we're going to call L, is given to be 380 nanometers. And we're asked what wavelength in the visible spectrum can we shine on here such that no light reflects, or that a minimum amount of light reflects. In order for that to happen, what's going to happen when you shine light on this sequence of materials here is that part of the incident ray here, labeled I, is going to reflect off the first surface, and part of it's going to reflect off the back surface. And if these two rays meet up and they're out of phase with one another, exactly half a wavelength out of phase with one another, then they're going to cancel out and you're going to have no reflection. So that means that the path length difference between these two rays, which here is twice this thickness as you go once to the right and once back to the left, this path length difference has to amount to some half multiple of the wavelength. So we said the path length difference is 2L, and that's going to be a half multiple of the wavelength. So I can write that as the wavelength times, and I'm going to write it like this, m minus 1/2. So m minus 1/2 means m here is an integer. So 1, 2, 3, etc. So m minus 1/2 will always be some half multiple of the wavelength. Now we have to be careful. It's not actually the vacuum wavelength. It's the wavelength in the material with index of refraction n, in this case n2. So I'm going to label it as lambda sub n so that you know it's lambda in the material, where lambda in the material is just the vacuum wavelength divided by the index of refraction of the material. Now there's one more thing we have to account for here, which is that you might have a phase shift at the reflections, or at the surface when you reflect. Because if you go from a lower index of refraction to a higher index of refraction, the reflected ray comes off phase shifted by half a wavelength. So that might offset everything, so we got to account for that. So let's look here. N1 to N2, we're going from higher to lower. So there's no phase shift here, so that's fine. Everything stays the same. But N2 to N3, we're going from lower to higher, which means that there's already a phase shift when you reflect off this back surface of half a wavelength. So we've got to add another half wavelength to get, well, what that does is it offsets this whole thing, this whole equation we wrote here. Well, it's going to be offset by half a wavelength. So we got to add another half wavelength to get it back to what we wanted. So we can add another 1/2 lambda, which is just going to cancel out this 1/2 lambda here. So we can just cancel this one out. So we have that 2L equals lambda n, which is lambda over n2, times some integer m. And m can be any integer, and we're going to have a minimum amount of reflection here. So now we have to solve for lambda and find which lambda is in the visible spectrum. So that's going to correspond to some value of m. So solving for lambda, I'm just going to bring everything that's not lambda over to the other side. I'm going to write the lambda first, actually. So we're going to have that lambda equals 2L times N2 over m. And if we plug the numbers in that we were given, this turns out to be 1,018 nanometers divided by m. Whoops. Well, the visible spectrum is from about 400 to 700 nanometers. So this is not in the visible spectrum, but if we divide this by 2, if we set m equals 2, So m equals 1 will give us 1018, so that's outside the visible spectrum. M equals 2, well, this is going to be about 500. That's in the visible spectrum. So set m equals 2, and we get that lambda equals, so 1018 nanometers divided by 2 is 509 nanometers.